Okay folks, last video in this module, and I think this is going to give us a lot of familiarity to our Gen Chem. We're going to talk about electron spin and the spin magnetic quantum number. So hopefully that will be familiar to you all from your days in general chemistry. And of course, we're going to add some extra P-Chem twists to it. So let's see, here we go. So to start, we will describe this Stern-Gerlach experiment. And in this experiment, conducted in 1921, they shot a beam of silver atoms through an inhomogeneous magnetic field in high vacuum. And the idea behind this was to investigate the spin and angular momentum properties of atoms, and something rather curious happened. So panel A gives us what the classical result would look like. So if we just take a bunch of atoms and expand them into vacuum, they're going to expand out like this. They're going to undergo Joule-Thomson cooling, right? They're going to do kind of this picture that we might expect. So, but what they noticed instead was on this phosphorus screen here, they noticed that there was a whole bunch of collisions of silver atoms with the screen in this position, and a whole bunch of impacts on the screen in this position. And so remember, there is a magnetic field going on here. So if this were expanded in just to a regular vacuum, no matter what the atoms were, they would do this. But now you can see the magnetic field influenced them. So they went on to propose that the electrons within those atoms have spin and thus create a magnetic moment. And particularly with silver, if you recall, its electron configuration goes as krypton, 4d10, 5s1. So it does have one unpaired electron, meaning it will be susceptible to a magnetic field. And so now we can begin to think of this in another right-hand rule arrangement, right? Where now I've got my spinning axis, I've got my radius, and now my magnetic moment points in the direction of my thumb, either in this orientation or in this orientation, right? So not, two right hand, left hand, it is another one of these right hand rules. And when we have a large collection of something like silver atoms, we would expect equal probabilities of them being either spin up or spin down, which is exactly what we saw here. So some electrons are spin up, some electrons are spin down. Another piece of evidence for electrons spinning is the appearance of doublets in various single electron atom spectra. So for example, in the hydrogen atom, which contains one electron, if we had a very, very high resolution spectrometer, we would actually see the appearance of doublets at each of these transitions. And those doublets are due to the fact that we would have some electrons spinning up, some electrons spinning down, and that subtle difference creates enough split in the energy level that we would actually get two transitions corresponding either to spin up electrons or spin down electrons. And of course, only in the case where we have atoms with unpaired electrons. Okay. So we can now begin to apply what we learned from the particle on a ring model to this notion that electrons are spinning. And without going through all of the rigmarole that we did, we can just cut straight to the results. So we can see that there's going to be this conical section, right, where we're going to have angular momentum projected on the z-axis, as well as total angular momentum. From that, we get this magnetic spin number, ms, which goes as s all the way down to minus s. So this is analogous to ml. Now the difference is, though, for electrons, there's only one spin quantum number, which is 1/2. So what that means is my ms quantum number, because it goes s all the way down to minus s in unit integers, that means ms can only take on values plus or minus 1/2, right? And so then what we can appreciate now is the component on our z-axis for electrons is always going to be 1/2 h bar. In the case of spin down, right, that's negative 1/2 h bar. And now my overall magnitude is going to be given by s times s plus 1 h bar. So that will be, let's see, can we do that math? 1/2 times 1/2 plus 1. So that's going to be 1/2. I should have had this like all written out, ready to go. So that is going to be root 3/4 h bar. Okay, so that length will always be root 3/4 h bar. And noting that it can either be spin up or spin down. And of course, we could come up with that angle theta from cosine of theta equals ms over square root of s times s plus 1. So all very cool. So if we now look at what the combined effect is, we can see this whole list of quantum numbers. So let's talk that out. So we have our orbital angular momentum quantum number and our magnetic quantum number. So if I go back to my simple picture here, here is my nucleus, and here is my rotational axis. Okay, so let's see, angular momentum on the z-axis is given by ml h bar. Okay, and of course, if we wanted to pitch that in and out of the theta plane, then we know that we start creating this other axis in L. But now what we can also start to appreciate, we've got this electron here that is also in itself spinning round and round. And so it is also going to have its own angular momentum in the z-axis given by ms h bar. So now when we look at those totals, that gives us quantum number J and quantum number MJ. So for example, in this picture where they're both oriented in the same direction, we're going to have this additive effect, right? If we look at the total angular momentum, that's given by L plus S. And then we can write its total magnitude as then the quantum number J as root J times J plus 1. So, so we'll flush that out in more detail in the live lecture. Okay, folks, that's it for this module. I will see you all later.